Okay, I think we're going to start. Are there questions?
Sir, I had something in regards to quantum mechanics in general.
Okay.
When we write down representations for Lorentz algebra, like we write phi as a scalar, we have the Dirac spinner and so on and so forth. But and we write down the transformation as some linear transformation, like phi under a Lorentz boost or something goes as phi of lambda x times a matrix S.
That's right. Yes.
But and so Schroeder, Peskin and Schroeder's book says that in general we could consider nonlinear transformations, but we can somewhat show that they can be reproduced using linear transformations or something like that. I don't understand that statement.
Okay. Yeah, I'm not sure exactly what the statement was, but the point is certainly you can have symmetries which are with nonlinear representation. Okay. But at least for the Lorentz group, I mean, the all known fields transform in the linear representation. Okay. I mean, another way of saying this is that the Lorentz symmetry is not spontaneously broken. Okay, because often the spontaneously broken symmetries are realized non-linearly.
I see.
And in fact, you will see that even the symmetries are not spontaneously broken, right? Like many non-abelian symmetries. Okay? That is inherently non-linear. Okay? So transformation law of phi, okay, may involve terms quadratic in fields and other higher orders. Okay? But it doesn't happen for the Lorentz group, for the Lorentz transformation. At least the kind of fields that you need to deal with, okay, they are all linear representation.
Also, like we also impose composition law, right? That lambda prime boost should be uh, like can be made by a single boost,
Yes, that's
or
right.
at least a Lorentz rotation. So that might not be true in non-linear cases.
No, see, composition law has to be true even in non-linear case, right? Because if you suppose you have two symmetries and you compose them, that is obviously going to be another symmetry, right?
Yeah.
Okay? So that has to be included as part of the symmetry, right? You may not call it Lorentz transformation, right? But if when you try to classify the full set of symmetries of a theory, okay, then it must satisfy composition law. Namely, if you compose two symmetries, it must generate another element of the symmetry.
Yeah, but it might not be a single transformation like a Lorentz transformation. Like if I compose a Lorentz transformation with a translation,
Yes,
that is also symmetry.
yes.
But it's not a single parameter sort of a thing, I think.
Well, it is saying, meaning if you take a specific Lorentz transformation and a specific translation, right? It's a specific transformation, right? You can write them as a single transformation, right? Which is in fact part of the Poincare group. So if
Oh
you
yeah.
find that composition of two symmetries take you out of the set that you have considered, right? That means that you have the symmetry generators transformations that you have identified are not the complete set of symmetries, but the complete set of symmetries will always form a group because you can always compose two and get another one.
Even in the nonlinear case.
Yeah, even in the nonlinear case.
All right.
Are there other questions? Okay, if not, let me begin. Okay, so let me briefly recall where we ended yesterday. So we are considering interacting scalar field theory. Okay, and the Hamiltonian, we wrote it as a sum of a free Hamiltonian and an interacting Hamiltonian. So the free Hamiltonian takes the form of a Klein-Gordon Hamiltonian, which is here. And for the interacting Hamiltonian, we have chosen phi to the 4 coupling. Okay, so there is a coefficient lambda over 4 factorial, and then you have integral of phi tr to the power 4. Okay. Then you went through a series of definitions. Okay. We defined H0, okay, as H free evaluated at T0. So by construction, H0 is time independent, right? Because H0 is defined as H free at T0. Then we defined this phi I and pi I, okay, by conjugation of phi by this field operator, okay, e to the I H0 T minus T0. Okay, so phi I Tr is e to the I H0 T minus T0, phi T0 are e to the minus I H0 T minus T0, and similarly for pi I. Okay. So if the interacting part was not there, okay, then of course H is H0, Okay? And this would be what you will call phi tr, right? That this will be phi tr according to the Heisenberg equation. Okay? But here, of course, that's not the case, okay, because we are only using part of the Hamiltonian. Okay? So we call it phi I. Then we define 0 as the ground state of H naught and omega as the ground state of H. And then we showed that if we try to calculate these objects, okay, the time ordered product of the phi i's, okay, and take the expectation value in the ground state of H0, okay, then these are given by the free field results that we have already learned to compute. Okay. And the way we showed this is by showing that H0, okay, can be expressed in terms of the phi i's, okay, simply by replacing pi and phi by pi I and phi I in this equation. Okay. Furthermore, pi I and phi I have the same commutation relation as pi and phi would have. Okay. So as far as these matrix elements are concerned, right, it behaves as if we are dealing with a free field theory. Okay. But these are, of course, not what you want to compute. Okay. What you want to calculate are these objects. Okay. The time ordered product of the phi's between the true ground state of the Hamiltonian or the full H. Okay. And our goal then was to express these objects, okay, in terms of the objects that you can calculate. Okay. And as we said, we will not be able to do this exactly, but we will be able to do this in a perturbation expansion in powers of lambda. Okay. But I should just also add that so far whatever we have done, okay, does not require lambda to be small. Okay, so far whatever you have done, okay, can be done for arbitrary lambda. Okay, because you are not saying anything like H interaction is small as yet. So then we went ahead and defined more quantities. So we defined ut as this. Okay, H naught is time independent by construction because it's a H free at T naught. H is time independent because H is a full Hamiltonian. Then we defined ut T prime as ut prime inverse. And then we found that what we want to calculate, okay, namely the vacuum expectation value, the true vacuum expectation value of the time ordered product of the phi's, okay, can be written in this form. Okay. So let me just briefly remind you what these are. N1 and N2 are constants. Okay, this will determine later. Okay. This is U, okay, evaluated. Okay, the first argument, okay, is for a complex time. Okay, it's T times 1 minus I epsilon. So I have used a different symbol T today, okay, not to confuse with the time ordering. I hope it's the distinction is reasonably clear. Okay, so this we have to take to infinity at the end, okay, and after you take this T to infinity, you have to take epsilon to 0, okay, from the positive side. Okay, but the order is important. We have to first take T goes to infinity limit and then take epsilon goes to 0 plus limit. So the first term here is this ut T prime, with the first argument being given by T times 1 minus I epsilon. Second argument is Ti1. Oh, I should have said that what are I1 to In? Okay, so given x1 to xn, okay, we can order time. Okay, and we have assumed that the time ordering is such that xi1 naught is the largest time, then xi2 naught, then xi3 naught, and so on, and xin naught is the lowest time. Okay, and that's what these things mean. So you have the u, then the phi I, okay, then another u, ti1, ti2, then phi I of xi2, and so on. And the final term is u tin, and the second argument is minus t times 1 minus I epsilon. So this is what we established. But we are still not done yet, right? Because what we can calculate are these. So the goal now is to try to express these u's, okay, u t prime in terms of the phi i's. You can see from this expression, right, that if we could express the u t prime in terms of the phi i's, then you are done, right? Because then everything that is inside is given in terms of the phi i's, and you are calculating the expectation value in the ground state of H0. So this will be our goal today, okay, that we will try to express u t prime in terms of the phi i's. And the way we will do it is that we will not try to calculate ut prime directly, okay, by calculating ut and ut prime separately and then computing this. Instead, what we'll do is to regard this as a solution of a differential equation and then solve the differential equation. Okay, and we'll see how it goes. So this is more or less what we had done yesterday. So are there questions on this? Okay, so if not, we'll proceed. Okay, so let me remind you that UTT prime is ut times ut prime inverse, and ut, the definition of ut was e to the ih naught t minus t naught times e to the minus ih times t minus t naught. And as we said, the way we'll try to determine this is by regarding this as a solution to a differential equation. So for this, let's first calculate du dt, okay, using this expression over here. So when you take the derivative with respect to time, there is a t here and there is a t here. When you take the derivative of this, you'll bring down a factor of ih naught, and that ih naught can be placed either to the left or to the right of this, right? Because h naught of course commutes with h naught. Here I have chosen to place it to the right of it to the ih naught t minus t naught. Okay? So that's the first derivative of the first term, and then of course you have to follow it by e to the minus ih times t minus t naught. When ddt acts on this, you bring down an h. Again, you have a choice of putting the ih or minus ih on the left or on the right. Here I have chosen to put it on the left. So minus ih here, and then to the minus ih times t minus t naught. Now you can take out, we can use this fact. So remember that h of t naught is, okay, let's look at this h. H of course is time independent. Okay, so h is the same as h of t naught. But h of t naught is h free of t naught plus h interaction of t naught. H free of t naught is h naught, and h interaction of t naught I have written as it is. So this difference then can be written as minus I times h interaction of t naught. And that's what I've done here. Minus I of course is a multiplicative factor which I can take outside. So is this clear so far? Okay. So let's proceed from here. So we are going to manipulate this. Now to manipulate this, remember that h interaction, okay, of course is a function of phi and pi. Okay, in the case that we are interested in, it's phi to the 4. Okay, but in general it's a function of phi and pi. So let's do things in general. Okay. So I can write h interaction of t naught as h interaction of phi t naught or pi t naught. Okay, namely phi and pi integrated over evaluated at t naught. Okay. R of course has to be integrated over. In the definition of h interaction, there is an integral over r. Okay. So the important point here is that I evaluate phi and pi at the time t naught. Okay. And then you have this e to the ih naught t minus t naught on the left and e to the minus ih naught t minus t naught on the right. Sorry, e to the minus ih t minus t naught on the right. So what I have done here is that I have multiplied and divided by this factor. So this product is of course just 1. Okay, so I have inserted this product. Okay. And then you have this e to the minus ih times t minus t. The reason that I have done this is because this combination I can now identify as ut again. Okay, from this definition. And here what we have is e to the ih naught t minus t naught, h interaction of phi pi, both evaluated at t naught, and to the minus ih naught t minus t naught. And now I claim that this is given by h interaction of this conjugation. I can take inside. Okay. It's given by h interaction of e to the ih naught t minus t naught, phi t naught r, e to the minus ih naught t minus t naught, and similarly e to the ih naught t minus t naught, pi t naught r, e to the minus ih naught t minus t naught. Okay. So let's see this, see how it appears for the simple case of phi to the 4. Okay. Imagine that h interaction was phi to the 4. Okay. So then this term, okay, h interaction of this will be given by the fourth power of this. Okay. But in taking the fourth part of this, you see that this e to the minus I h naught t minus t naught from the first factor of phi will cancel the e to the I h naught t minus t naught from the second factor of phi. Similarly, this from the second factor will cancel this from the first factor. So at the end, what we are left with is 1 e to the I h naught t minus t naught at the extreme left and 1 e to the minus I h naught t minus t naught to the extreme right. And that's what we had here. So, and this you can argue for any product of phi's and phi's, okay, because this will always cancel. So because of this, I can rewrite this h into this. I can take this conjugation into the I h naught t minus t naught and into the minus I h naught t minus t naught inside the argument of H interaction. Is this clear to everybody?
Please repeat the derivation du by dt again.
Okay, so up to this point, it's clear?
Yeah, I am cleared about the above step. Du by dt is equal to minus I e power I h naught into t minus t naught into h interaction into e power I minus I h t minus t naught. Up to that point, I am clear.
Okay, so this part you, okay, the next line you want to see.
Yeah.
Okay, by the way, can you see my cursor moving? If I move,
Yes.
you can see it?
Yeah, yeah.
Okay, because if I point a line, yeah, okay. So this is the line you are worried about, right?
No. Above line.
This one.
Yeah, above. That I'm worried about the commutation relation of pi and pi of t naught r and pi of t naught r.
Oh no, sorry. This is not commutation relation.
Okay.
I'm sorry. This is a function. H interaction is a function of this.
Okay.
Yeah. Sorry, this is not a commutation relation. Maybe like that I should have used a different symbol here. After that, everything is clear.
Please explain again.
Okay, here. Okay, so let me try to do this. Okay, so first of all, what we are seeing here, there is not commutation relation, right? So now I can't write. Okay, can you see this?
Yes, sir.
Okay, so we had e to the I h naught t minus t naught, then H interaction, which is a function. Okay, I am writing this bracket. Say phi t naught r and pi t naught r, and into the minus I h naught t minus t naught. Okay. So let's do the function. Say phi to the 4. That's what we had, right?
Yes, sir.
So then we have e to the I h naught t minus t naught phi. I'm not writing the r argument, okay, but there's a r argument. Phi t naught to the power 4 e to the power minus I h naught t minus t naught. Okay. Now this is a product of 4 phi's, right? Now what I'm saying is that I write it as a product of 4 phi's, and this product I'll write as phi t naught e to the power minus I h naught t minus t naught, then e to the I, well, unfortunately I'm running out of space. Let me see if I can erase everything. Okay. So if we have phi t naught to the power 4, okay. So what I'm saying is that I write this first of all as phi t naught, and 4 times. Okay. Then I'm going to insert here a factor of e to the power minus I h naught t minus t naught e to the power I h naught t minus t naught. Okay, between every pair of phi's. Is this clear?
Yes, sir.
Okay. So now you see the first phi, right? There is already an e to the I h naught t minus t naught sitting on the left, right?
Yes, sir.
Okay. So that times phi t naught times e to the minus I h naught t minus t naught, that will be there. Okay. The next term will be e to the I h naught t minus t naught, phi of t naught e to the minus I h naught t minus t naught.
Yes.
Okay. So this way, every phi t naught will be replaced by e to the I h naught t minus t naught, phi t naught e to the minus I h naught t minus t naught.
Yes, sir.
Is that clear?
Yes, sir.
Okay. So let me go back to the screen. Okay, so this is what I have said here, right? That H interaction, so it was a function of phi t naught and pi t naught, right? In fact, forget about pi t naught now because pi is not really there. Okay, it's a function of just phi because phi to the 4 is what we are considering. And this, even though we had only e to the I h naught t minus t naught on the left and one e to the minus I h naught t minus t naught to the right, you can rewrite this as if this acts on every factor of phi. Is that clear?
Yes, sir.
Okay. So here, for example, H interaction of phi I tr. Okay. Forget about pi I. So this means phi I to the 4, right?
Yes, sir.
So each phi I is this.
Yes, sir.
So if you raise to 4th power, all the intermediate factors of e to the I h naught t minus t naught e to the minus I h naught t minus t naught, they will cancel out. Okay. And you will be left with 1 e to the I h naught t minus t naught on the left and 1 e to the minus I h naught t minus t naught to the right. So that's this manipulation.
Okay, sir. Okay.
Yeah.
Okay, sir.
So any other question here? So what we get at the end of this is that du dt is given by minus I h interaction, okay, the arguments being phi I and pi I, okay, times u of t. Okay, because this combination is u of t. Okay. And just so that you don't have to write this every time, but let me just emphasize again that this is not a commutator. Okay, this is simply saying that it's H interaction as a function of phi I and pi I. Okay, I'll change this in the notes to some other bracket. So let's define HI, okay, as H interaction with arguments phi I and pi I. Okay. And so what we get, so this equation that we have gotten, okay, can be rewritten then as du dt equal to minus I hi of t u of t. Is this clear?
Yes, sir. Yes, sir.
Okay. So now we are interested in UTT prime, right? Not UT directly. Okay, but UTT prime is UT times UT prime inverse. So using this, we get this partial derivative. Now it's a partial derivative because U is a function of t and t prime. So I have written as a partial derivative. So del U del t, okay, is du dt times ut prime inverse, okay, because this acts only on the t argument here. So that gives you minus I hi of t u of t, and then you have ut prime inverse. But that's nothing but minus I hi of t ut t prime. So this shows that ut prime satisfies this first order differential equation. Now to solve a first order differential equation, you also need a boundary condition, right? In fact, you need a single boundary condition. Okay, for since U is a matrix, okay, you have to specify U as a matrix or an operator, okay, at some particular value of time. And that is easily done because from the definition it follows that at t equal to t prime, U is identity matrix. So U T T prime is identity at t equal to t prime. So what have we done? Okay, we have basically taken the original expression for U that we had here and shown that that expression for U satisfies a certain differential equation which is here with a certain boundary condition which is here. And now the point is that because a first order differential equation has a unique solution once the boundary condition is satisfied, so the single boundary condition is satisfied, it is enough to determine U by simply solving this equation. Or if I give you an expression for U and tell you that this is the correct expression for U, all you have to check is whether it satisfies the boundary condition and whether it satisfies the differential equation. Because once it satisfies the boundary condition and the differential equation, it's determined uniquely. And since we know that U satisfies this equation, that U that I have given you must be the U that you have. Is this logic clear? So this is the logic we are going to use to determine U. Any questions? Okay, so if not, we are going to proceed. So here is a summary again. Okay, that U T T prime is determined from this equation. Okay, the differential equation del U del T is equal to minus I H I T times U T T prime. H I T, again let me remind you, is short form for this. And U T T prime must be identity at T equal to T prime. Now I claim that U T T prime is given by this. It's a time ordered product of exponential of minus I times integral T prime to T H I T double prime dt double prime. We'll prove this by showing that this satisfies the differential equation and the boundary condition. But of course, to prove this, you have to first understand what it means. Okay, what do you mean by time ordered product of an exponential? So there are many ways to describe this, but I'll give a more practical version, which is useful, and that is to simply expand the exponential. Expand the exponential in the power series, which is here, and then put the time ordering over every term in the product. So if you didn't have the time ordering, right? Suppose you had exponential of a, then you would have written 1 over m factorial times a to the m. So a to the m will be integral dt1 hit1 integral dt2 hit2 up to integral dtm hitm. And now what I'm saying is that the definition of this is that you put the time ordering now on the product of this. Okay, so are there questions? Is the definition clear?
Sir, but because of the time ordering, we are not integrating over the full region. We are only integrating over some part of the region. Or is it?
No, we are integrating over the full region, right? See, T1, for example, is always integrated from T prime to T. T2 is always integrated from T prime to T. But in different regions, these operators are ordered differently, right? In some region, T1 is larger than T2, in which HIT1 will be to the left of HIT2. Right? In some other region, T1 is less than T2, right? In which case, HIT2 will be to the left of HIT1.
And do they commute? They don't commute.
No, they don't commute. Right? They don't commute, exactly.
Okay.
They don't commute, right? But that's the definition of time ordering, right? See, inside the time ordering, it doesn't matter which order you write this. Because the ordering of operators is determined by time ordering, right? So I could have written this HITM to HIT1, okay? Reverse order or any arbitrary random order. It doesn't matter because time ordering fixes the order of the operators.
Okay, so if they did commute, then it would be the same as no time ordering.
Exactly. If they did
Okay.
commute, then it doesn't matter how you ordered them, right?
Okay.
Okay. So time ordered product of AT1 times BT2 okay, is the same as time ordered product of BT2 times AT1. Okay. Even if B or BT2 and AT1 doesn't commute. Okay, because that's the definition of time ordering. Because whether AT1 is to the left of BT2 or to the right depends on the ordering of T1 and T2. Right? Doesn't matter where you have placed them in the product. That's why time ordered product okay, of phi x1, phi x2 is symmetric under x1, x2. Okay, this we had seen, right? Delta of x1, x2, which is the expectation of the time ordered product of phi x1 times phi x2, is symmetric under x1, x2 exchange. Even though phi x1 and phi x2 doesn't commute.
Okay.
Okay, are there other questions? So is the meaning of this clear? Okay. So let's call this expression VTT prime. Okay, because we want to show that this is equal to UTT prime, but we don't know it yet. Okay, we have only claimed that this should be equal to UTT prime. So let's call this VTT prime. Okay. And our goal will be to prove that UTT prime is the same as VTT. Okay. So what do you have to do to prove this? Okay. We have to prove first of all that VTT prime satisfies the boundary condition here, okay, and that VTT prime satisfies this differential equation. Okay. And we will do this in turn. Okay. So the first part is easy. Okay. To show that it satisfies a boundary condition. Because at t equal to t prime, right? You look at the expression of t equal to t prime, right? At t equal to t prime, all these integrals are just gone. Okay. So any term from m equal to 1 onwards just vanishes because the integration range tends to 0. Okay. So only the m equal to 0 term contributes. But m equal to 0 term, of course, is just 1 here, right? No operator here. So that's just identity. Okay. So indeed at t equal to t prime, v t prime is identity. Is this point clear? Okay. So the second part is a little more involved, so I'll go through it carefully. We have to now check, we have to calculate the derivative, del v del t. Now let's look at the expression for v. This is v. Okay. So where is the time dependence in v? The time dependence, as you can see, is in the limit. So time dependence, the t dependence is in the limits. So you are trying to differentiate an integral with respect to its limit. Okay. Now, when you take a differentiate an integral with respect to its limit, right? The rule is that you simply remove the integral and replace in the argument the integration variable by the limit at which you are differentiating. So this means that when you take the derivative with respect to t, okay, in turn, okay, either here or here or here in turn, okay, we have to drop one integral, okay, and replace the corresponding t1 by t. Okay, so for example, if you take the derivative of this, okay, then the rest of the integral will remain and hi of t1 will be replaced by hi of t. If you take the derivative here, okay, then everything else will remain. So this integral will be dropped, okay, and hi of t2 will be replaced by hi of t, okay, and so on. Is this clear? But now you notice that all of these terms are actually the same. Why is it the same? Okay. Let's suppose that we are taking the derivative with respect to t. Okay. So this is hi of t, right? And these are hi of t2 to hi of tm. So this integral will be gone and you are integrating from t2 to tm, okay, with hi of t sitting here. Now suppose you are differentiating this term. Okay. Then the T2 integral will be gone. So you have hi of T1 and then hi of T, hi of T3 and so on. Okay. But of course, the integration variables, okay, T1, T3 up to Tm, okay, you can rename as whatever you want, right? You can rename them as T1 to Tm, for example, okay, or sorry, T2 to Tm. Okay, you can just replace T1 by T2, okay, and be done with it. Okay. But it still not doesn't look the same because here, okay, we had hi of T, hi of T2. Okay. Now we have hi of T1, which has become hi of T2, and hi of T. Okay. So they don't look the same. But as we discussed inside the time ordering, okay, it doesn't matter which order you write the operators. Okay. They are the same. hi of T1, hi of T is the same as hi of T, hi of T1. So because of this, right, every derivative, okay, whether you take the derivative here or here or here, okay, they give identical result. Okay. So that gives a factor of m. Okay. So what we can do is that we can put a factor of m here, okay, and then take only one of the derivatives, right? You can take del del t, act on any of these. Okay. And I'll just choose to act on the last one. Okay, on this one. So the result will be then I have the T1 to Tm minus 1 integral intact. Okay. And this Tm here will be replaced by T. Is this argument clear? Any question? Okay. So here is it. It is. Okay. Sorry, here it is. I have taken multiplied by m, okay, kept the integrals over T1 to Tm minus 1, okay, all from T prime to T. Okay. And then I have a time ordered product of hi T1, hi T2 up to hi Tm minus 1 times hi of T. Okay. But let me emphasize again that it doesn't matter where you write this hi of T. It could be either on the extreme left or here or here. Okay. In fact, that's the way different terms have HIT in different places, right? But because all of them are the same, I have just written it at the end. So this gives you minus I to the m over m minus 1 factorial. Okay, this m cancels this m factorial, I get m minus 1 factorial. Okay. And I have written this a minus I to the m minus 1 by pulling 1 minus I outside. But now we look at hi of t. You see that in these integrals, okay, all the time arguments run from t prime to t. Okay. So t is the largest time. Okay. None of these arguments, okay, are larger than t. Okay, because each of these run from t prime to t. Okay. So t is the largest, so that means that when you actually expand it out, okay, hi of t always sits on the left, on the extreme left. So you might as well write it on the extreme left. Yeah, that's what I have done. Okay. I pulled hi of t out of the time ordering, and I've written it as hi of t times time order product of h1 t1, h2 t, hi t1, hi t2 up to hi tm minus 1. Is this clear? This step? Okay. So now we are done. Right? We have minus I HIT. Okay? And this sum, okay, just by calling m minus 1 as m. Okay? You see the m equal to 0 term had gone from here because when you take the derivative, m equal to 0 term is just 1. So that term goes away. Okay? But now you define m minus 1 as your new m. Okay, so the new m again runs from 0 to infinity. And we get back minus I to the m over m factorial. Okay, which is this. And this T1 to Tm because m minus 1 I'm calling m. Okay? So that's exactly VTT prime. So this shows that V indeed satisfies the del VTT prime del T is minus IHIT times VTT prime. Okay? So this was the required differential equation. Okay? So now given that V satisfies this differential equation and in this boundary condition, okay, we can conclude that UTT prime must be the same as VTT prime. Okay, namely UTT prime is given by this expression over here. Are there questions? Okay, so we'll proceed. So let me then summarize the results again. So what we have established so far is that this matrix element, okay, which is what we want to calculate, is given by this normalization n1, n2 inverse, and then the expectation value, okay, this time in the ground state of H0, of this ut1 minus I epsilon ti1, etc. And utt prime, okay, this is a new ingredient. The utt prime, okay, we have established, is given by time order product of exponential minus I integral t prime to t hi t double prime dt double. And hi of t, let me remind you again, is h interaction evaluated with the arguments phi itr and pi itr. So now what we are going to do is to substitute this expression for u inside this. Each of these u's I'm going to replace by this integral. So that gives a big expression which I have written here. But this expression is nothing but u written explicitly. So you see that it alternates between the u expression, then phi, then another u expression, another phi, and so on, and finally one u expression that takes you from tin to minus t times 1 minus I epsilon. So is this step clear? Any question here? Okay, so now you notice that in this product, right, this is time ordered automatically, okay, by definition, because this is t of this. Then comes phi I of xi1. Okay. This is not a priori time ordered with respect to the others, okay, because you have already, among the phi's you have already time ordered, okay. xi1 is larger than xi2 and so on. xi1 not is larger than xi2 not and so on. But now let's look at the relative times between here and here. Okay. This time here runs from ti1 to some large number. Okay. So every t double prime that appears here, okay, is larger than this, larger than xy1 naught, right? This is ti1. Okay. So every time argument that appears here is larger than ti1. Similarly, ti1 is larger than every time argument that appears here, because here the time argument runs from ti2 to ti1. Okay. Inside this it's time ordered, okay, but it was a priori not time ordered with respect to this. Okay. But we see that the way the operators appear, actually they are already coming time ordered, okay, because t double prime can only go from ti2 to ti1. Similarly, this time that you see here, okay, is smaller than all of the times which are to the left. Okay, xi2 of course is smaller than xi1. That was by design. Okay. But look at the time arguments here and here, right? They run from ti2 to t. All of these time arguments are larger than ti2. So this product that you see here is already coming time ordered, which means that you can just write it as a one single time ordering instead of multiple time ordering, right? Here you have a time ordered product, then an operator, another time ordered product, another operator, another time ordered product, another operator, and so on. But you can just write it as a single time ordering, okay, and product of all the operators inside. Is this point clear?
So
Yes.
As a technicality, like integrating something like the first and the last terms,
Yes.
from a real number to a complex number, it isn't really a suitable integral, right?
Well, you can define this in the sense of analytic continuation, right? Because this hi of t prime, I mean, you can in principle define it, right? Because after all, we'll see that we'll express all of these in terms of the delta f's, right? And delta f's are given as analytic functions of t and t prime.
Yeah, but I'm only saying that as an integral, it does not really. I mean, I'm not
We
sure
can
whether
think of this as a complex integral in the contour integral in the complex plane, right? In the complex plane, if you have two points A and B, you can integrate, right? Along some contour between A and B.
Yeah, you have to also select a path.
Yeah, you can select a straight line path, for example, right? See, this is almost on the real axis. Okay. So this will be a straight line path which is slightly tilted.
Yeah.
Okay. So I'll give a better prescription a little later, right? But at this stage, you can think of this as this is a point on the real line, right? And this is some point at a very large value, right, with a slightly imaginary part. Okay. And you can just connect them by a straight line and do the integral. Okay. And small deformations of that contour will not make a difference because this is analytic, right? There is a singularity of this in between these two lines, these 2 points. Okay. The singularities will come when this becomes close to some other phi, right? But that is not happening here. Okay, so what we can show is that this is actually invariant on a small deformation. That's why cos is integral formula. Okay.
Yeah.
But you don't, if you don't want to use it, just use the fact that you take a straight line path.
All right.
Okay. Any other question? Okay. So this is what I have done here, right? I've written the time ordering outside the product. Everything else is remaining the same. But now we are going to use the fact that inside the time ordering, the order of the operators don't matter. I could have written the order operators in any order that I like, because time ordering will automatically fix the ordering. Okay, T of AT1 BT2 is the same as T of AT2 BT2 AT1. So using that, I can put these phi's in any order I like. I can put these in any order I like, and that's what I've done here. Okay, so I have written the phi's here as phi I x1 to phi I xn, and I have combined all these integrals of all these exponentials together into a single exponential, which is here. And the understanding is that once we expand the exponential and write it as write it in this form, for example, what we did last time here. Okay, once we write it in this form, okay, time ordering will automatically place the time arguments, okay, the order the operators where they are to begin with. Okay, like here, for example, to begin with, they are in a certain order, right? That will automatically happen, okay, if you write it as a single exponential, okay, and if you expand it out, okay, because for different ranges of t double prime, okay, the operators will actually be placed in different places, okay, because there is time ordering sitting outside. But just as a compact expression, this looks much nicer than writing all these products. Is this point clear? So normally you cannot combine exponentials of operators, right? That I think you are familiar with. E to the a times e to the b is not the same as e to the a plus b, if a and b do not commute. But inside time ordering, that problem is not there, okay? Because that's the definition of time ordering, that if you have e to the at1 times e to the bt2, that's the same as e to the at1 plus bt2. Because once you expand it out, time ordering will fix the ordering anyway. Okay, so if there are no questions, I'll proceed because we are going to start with this. Well, we are going to make use of this now.
So the issue isn't only with time ordering; it's also with non-commutativity.
Well, phi I x1 and phi I x2 don't commute, right?
Yeah, phi I is just fine, but while combining two exponents of operators,
Yes.
we also have like an infinite series of commutators.
But see, those commutators will all be zero inside time ordering, right? Imagine that you have time ordered product of AT1 BT2 minus AT2 BT2 AT1.
Oh, okay.
Right? That is zero.
Yeah.
Is that clear? Should I write? Maybe let me try it. Okay. So the claim is the following, that if you have T of AT1 BT2 minus BT2 AT1, this is 0. Okay, why is it 0? Because suppose T1 is larger than T2. Okay, then it's AT1 BT2 minus AT1 BT2, right? Because in the second term, okay, you have to reverse the order. If T2 is larger than T1, then it's AT1 BT2, sorry, then it's BT2 AT1 minus BT2 AT1. So in either way, this difference is always 0. Okay, so that's why the commutators you can ignore inside time ordering. Okay, even though phi x1 and phi x2 do not commute.
All right.
Okay. Any other question?
Sir,
Yes.
sir, instead of as you have prescribed the solution and then we check that it's indeed correct.
Yes.
If we solve the differential equation explicitly and get a solution of UTT prime,
Yes.
then we have to introduce time ordering by hand, isn't it?
No, see, it will automatically come because of the fact that when you differentiate, right? Look at the differential equation. Because the differential equation has HI sitting on the left, okay, the solution for UTT prime will automatically include a time ordered product of operators. If HI had been on the right, then you'll get anti-time ordered product. So it's not that you have a choice. When you try to integrate this, in order that this you satisfy differential equation where HI of t is to the left, right? You automatically have a time ordered product. See, if HI was constant, then it doesn't matter, right? Then the time ordering has no effect. Then you could have just taken this H naught as outside. But as long as HI is time independent, the solution to this is time ordered product of this.
Okay,
Not that
so
you could have avoided time ordering if you just try to directly solve it. Is this clear?
yes.
Okay. Imagine that you start from T prime, okay? And you solve it by saying that you first go from T prime to T prime plus epsilon, then T prime plus epsilon, T prime plus 2 epsilon, and so on. Okay. When you go from T prime to T prime plus epsilon, okay, you will multiply by some 1 minus I epsilon hi of T prime, right? You start with 1. Okay. At T prime plus epsilon, you will get 1 minus I epsilon. Maybe I can do it again. Okay. Then imagine that you have U T prime equal to identity at T prime equal to, sorry, at T equal to T prime. At T equal to T prime. Okay. So you calculate U and you have other equation del U del T equal to minus I hi of T ut T prime. Okay. So what will be U of T prime plus epsilon? This will be 1 or identity minus I epsilon hi at T prime, right? Okay.
Yes.
Then when you try to calculate U of T prime plus 2 epsilon, okay, you have to have, you are multiplying by minus hi on the left. Okay. So you'll get 1 minus I epsilon hi of say T prime plus epsilon multiplying 1 minus I epsilon hi of t prime. Okay, so you see the hi of t prime plus epsilon has already come to the left of hi of t prime. Okay, so when you try to integrate it by step, right? You first go from u t prime to u t prime plus epsilon, then you go from u t prime plus epsilon to u t prime plus 2 epsilon. You automatically get this time ordering because hi is on multiplying from the left. You can try to work this out explicitly and you will find the time ordering will come automatically. Okay, it's not that you have to put it in by hand. And you can also see it because I have already argued that the solution is unique, right? So once you have one solution, you cannot have another solution. So it couldn't be that both time ordered product and anti-time ordered product are solutions to this equation. Is this clear?
Yes, sir. Thank you.
Any other question? Okay. So I think we have gone through this. Okay, so this is the expression we found. Okay, this is we have written the same thing again. And this is just an expansion of that. Okay, I have just expanded this out as in the sum over m, okay, and written this as at the expectation value of phi i's, okay, and hi of t1 prime to hi of tm prime. Okay, and this t1 prime to tm prime are all integrated from minus t times 1 minus I epsilon to plus t times 1 minus I epsilon. Okay, and the point is that so this now is explicitly calculable because we have got the phi i's and hi is what are hi's? Hi is h evaluated with arguments phi I and pi I. So we have achieved our goal, right? We have taken the original expression and rewritten in a way where we can write it as an in terms of the vacuum expectation value. This time the expectation value in the ground state of H0, okay, of the product of phi i's, okay, because hi's are in fact the product of phi i's. Okay, so I'm going to write this more explicitly below. Okay, but let me just now say one thing which may address Kaustubh's worry. Right? So you see that here it's a little inconvenient because the t primes, right, run from minus t times 1 minus I epsilon to t times 1 minus I epsilon. So you can imagine that this is running along some tilted contour in the complex plane. Okay. Whereas the t's, right, the arguments of phi i's, they are sitting on the real line. Okay. Now you can avoid this by saying that we will just also replace ti's by ti times 1 minus I epsilon. Okay. This in fact has no effect because ti's are all finite, right? So if you know to take the capital T, okay, these t to infinity, okay, ti's remain finite. So eventually when you take the epsilon goes to 0 limit, ti's come back to the original real values anyway. Okay. So this is not necessary, but if you do this, okay, then what it says that you have a slanted contour. Okay, maybe I can draw it again here. Okay. So in the time coordinate, if I draw, say this is real t versus imaginary t, okay, we'll have a slightly slanted contour. Okay, so this is minus t times 1 minus I epsilon. This is a positive imaginary part. This is t times 1 minus I epsilon. Okay, and all the t's, all the intermediate insertions are sitting on this line. Okay, this is just a convenient to have representing it. Then you can think of this. There's a parameter u that runs along this line. Okay, and you can simply say that the integral that we'll be doing is over u, okay, which is running on from minus t to plus t. This is certainly not necessary, but this just makes the visualization a little easier. Okay, of what is happening.
Sir, do we encounter any singularity when we rotate uh, uh, the ray clockwise?
So as long as you rotate it by a little amount here, right, we don't encounter singularities. As you know, the singularities come when the arguments coincide or when they go on each other's light cone, right?
Yeah, so we can simply put the contour to be imaginary axis.
Yeah, we can do that, but that we'll discuss maybe later. Okay, I'm not sure if we'll do it in this course. Okay, it's certainly in quantum field theory 2, we will discuss this. Okay. But we could take it all the way to the imaginary axis, but let's not do it right now, right? Let's just think of this as slightly tweaking the contour so that you have a real integral. Okay, so that each of these you can think of as integral over u. Okay, these ui variables running along the real line.
Okay, sir.
Okay, any other question? Okay, but if this is, if you don't like this, you don't have to do this, right? You keep it like this. Okay. In that case, you have to just remember that these t prime integrals run over slightly tilted contour, or maybe you can take it all the way along real axis and only near the end you tilt the contour towards t times 1 minus I epsilon minus t times 1 minus I epsilon. And in the intermediate stage, you have this. Okay, so now let's look at the current problem. Okay, in the current problem, okay, hi is given by phi I to the 4. So you have lambda over 4 factorial, then integral minus t times to 1 minus I epsilon to plus t times 1 minus I epsilon dt prime dq bar prime times phi I to the 4. Okay. So what we have here, we have a product of the phi i's. Okay, these are the phi I, these are x1 to xn were the arguments that we started with. They are here. Okay. And then you have gotten some intermediate integrals, right? Depending on what order you want to calculate, right? So each part of each hi comes with a lambda, right? So this is where the perturbation expansion becomes important. If we want to calculate up to any given order in lambda, okay, you keep those many hi's, okay, say lambda to the 4, okay, you keep up to 4 lambdas, okay, so give 4 hi's, okay. Then each of those are integrals of phi I to the 4. Okay. So ultimately then what you have to calculate, okay, are the time ordered expectation value of the time ordered product, okay, in free theory, okay, or the product of phi i's, right? Product of the original phi i's as well as some of the phi i's that are coming from the hi's, okay, which you see from here. And these, as we have discussed, can be calculated using the free field correlation function, Green's functions, because we have already established that if we take the product, time ordered product of the phi i's and take the expectation value in the ground state of H0, they are just given by the ordinary product of ordinary Feynman propagators that you have already found before. Okay. So this, for example, is given by this plus all equivalent pairings of these x1 to x2n. So is this point clear? Okay. So the upshot is that we can express what you want to calculate in terms of what you know how to calculate. Okay. And what you know how to calculate are these objects. Okay, because hi's are just written in terms of the phi i's. Okay. So here I should add a caution, okay, that we have this composite operators phi I x prime to the 4, right? So because of this, you have seen that because of this composite operators, there will be divergent terms like delta f x prime, okay? Because some of these x's, suppose you take x prime to x prime, right? Delta f x prime, that is divergent, we have already seen. Now we can avoid this, okay, by normal ordering. Okay, we can say that in the expression for hi itself, we'll put as normal ordered phi I to the 4. Okay, you can do that, but unfortunately that doesn't remove all the divergences. Okay, so for now, let's not worry about the divergences. Let's keep it as it is. Okay, and later on, okay, I'll discuss how the divergences are actually taken care of in quantum field theory. Okay, the full details you will see only in the second course on quantum field theory, but I'll at least try to explain, okay, what is the general principle by which you avoid divergences of this kind in quantum field theories. Are there questions?
So can you again explain the source of the divergence?
Source of the divergence?
Yes, yes.
Okay. See, you have here phi I x prime to the 4, right? Let's call this x prime. Okay. So let's imagine that we are calculating to order lambda. Okay. So you have 4 phi's here. Okay. Phi I x1 to phi I x4. Okay. Say, and a phi x prime to the 4. Okay. Now, what are you supposed to do? You are supposed to calculate this by using this formula, right? That you have to calculate delta f, all possible delta f, all possible laws of pairing. Okay. So some of these pairings will involve, say, there is a phi x to the 4, right? That means 4 factors of phi x prime, right? So some of these pairings will have both arguments x prime. Is that clear?
Yes, sir. Yes, yes.
So if you have both arguments x prime, right, then you get a delta f x prime, right? And that you know is divergent. We have seen already that when the two arguments are on the right cone, right, then they diverge. So in particular, when they coincide, this delta f diverges. So that's the source of the divergence, right? It's actually infinite, delta f x prime. Is that clear?
Yes, sir. Yes.
Any other question? Okay. So now remember that we are not done yet. Okay. Why are you not done yet? You have this factor n1, n2 inverse, right? We can calculate this, okay, by what we have said, but you still have to calculate this. Okay, so let's try to do that. So the way to calculate this, of course, we have written down an expression for n1, n2, but that expression is not very useful. We'll calculate this by making use of this equation itself. Okay. So let's look at this equation, okay, and set n equal to 0 on both sides. Right? This is valid for any n, right? So even if you didn't insert any operator, okay, it should still be valid. So let's set n equal to 0. Okay, no operator insertion. Then the left hand side is just inner product of omega with omega. That's of course 1, right? Because omega is normalized. So that gives you an expression for n1, n2, right? Because that gives you 1 equal to n1, n2 inverse times something that you know. Okay. So this gives n1, n2, okay, as this sum, okay, and the same expression except that this term is absent, right? There is no product of phi i's because n is 0. So we just have the product of time order product of either h i's. Okay. But this of course can also be evaluated with Feynman diagrams, right? Or if you don't like Feynman diagrams, right? I think some of you may not still be very familiar with Feynman diagrams. Okay. Each of these is phi I to the 4, right? So you have an expression like this. Okay, so you just apply this formula again. Okay. Feynman diagrams, okay, let me again emphasize that, I mean, if you are not very comfortable with Feynman diagrams are nothing but ways to calculate this, right? Ways to organize this, right? If you don't like Feynman diagrams, you can always use this formula. Okay, it's just much harder work if you try to use this formula because you have to keep summing over all equivalent pairings, right? Feynman diagrams essentially give you organizes this sum in a neat way. Okay, and we'll see some examples, if not today, tomorrow, let's say. So are there questions?
Sir, so what problem would have happened if we had not taken this 1 minus I epsilon?
Well, at this stage, we don't see the problem. We had to take this to begin with, right?
Yes.
Okay. Then you have to worry about whether this integral converges or not, right?
Yes. So as long as we are taking perturbation, it converges, or
no, you still don't know, right? Because we know that delta f's are finite for finite argument, right? But now we have to take some of the arguments to infinity, right?
Okay.
Okay, but we'll see that what happens at the end, right? It will converge, right? Provided, we'll see that this I epsilon actually is related to the I epsilon that we had in the expression for delta F in the first place.
Okay.
Okay, but at this stage, since our analysis gave us this expression, let's keep it this way. Okay, so even though I'll often call this d4x, okay, this integral I'll use a short form as d4x prime. Okay, but it should be understood that the x naught prime, right, the time argument should go from minus t times 1 minus I epsilon to t times 1 minus I epsilon. Okay.
Okay.
At the end, we will see how to drop this. Okay, but we need some I epsilon prescription even there. Any other question? Okay, so let me then summarize what you have gotten. So you are trying to calculate this. Okay. The expectation value of this between the vacuum state, okay, the true vacuum, the ground state of H. Okay. We saw that this can be written as a numerator divided by denominator. Numerator is this. Numerator is here. Okay, this is what I'm calling the numerator. Okay, other than this n1 by n2 factor, this rest of the expression is what I'm calling numerator factor. Okay, this can be evaluated by using this. Okay. But you can also write this as a sum of Feynman diagrams. Okay. So this will be given by Feynman diagrams whose vertices include n external points. Okay, vertices are the place where the short lines come out. Okay, that's the role of the vertices or the points. So it includes n external points, okay, each of which has one line coming out. This was the rule for Feynman diagram that we had said. Okay. And it has also m internal points, each of which will have 4 lines coming out. Okay. Why 4 lines? Because you have phi I to the 4, right? That's all. Because you have phi I to the 4, right? This corresponds to 4 phi lines coming out from an internal point. Okay, and that's the way you should draw the Feynman diagrams. Okay. And then the rule is that you draw all Feynman diagrams. Okay. The expression that we associate with the Feynman diagram, okay, first of all has this factor minus I lambda over 4 factorial to the m. Okay, let me describe where that comes from. Okay. That comes from because there's a minus I to the m over m factorial. Okay, that's this, and each hi has a factor of lambda. Okay. So if there are m hi's, you'll have lambda to the m. Sorry, lambda over 4 factorial to the m. Each hi has a lambda over 4 factorial. Okay. So that's what I wrote here, minus I lambda over 4 factorial to the m. Then you have the propagators. Okay. And then you have the combinatoric factors. Okay. These combinatoric factors will typically include, okay, maybe I should have written that separately. Okay. There's a 1 over m factorial. Okay. If you have m internal vertices, okay, namely m phi I to the 4th, okay, then you have also a 1 over m factorial. Okay. Then you have propagators, and then you have the combinatoric factors. Okay. Combinatoric factors we had seen is the number of ways a given Feynman diagram can appear. Okay, and I think this you will learn only by doing examples. Okay, and we will do some of the examples in a few minutes. Okay. After you do that, okay, then you have to integrate over the space-time coordinates of internal points. Okay, and that refers to the fact that you have the integral over t primes, okay, here, and each hi also includes integral over the x's. Okay, so here, for example, we had, let's see where I have written. Yeah, we have integration over the time as well as the space coordinates, right? Because Feynman diagrams only take care of this part. For the denominator, we have exactly the same rule, except that there are no external points, right? Because denominator involves no external phi's, right? This term is absent in the denominator. Okay, that's as you can see. Okay, so let me do a Feynman diagram anyway, and then it will become clear. Okay, so let's suppose that we are considering the case n equal to 4, m equal to 1. Okay, so what is n and m? N means that we are calculating a 4-point function. Okay, phi x1, phi x2, phi x3, phi x4. Okay. M equal to 1, okay, means that in this numerator, that in this expression, okay, I'm using the m equal to 1 term. That means only one insertion of hi. Okay, one insertion of hi means this integral, this phi I to the 4. So let me explain now how you represent this in the Feynman diagram language. So the Feynman diagram has 4 external phi's, external legs, right? So each of these you can see has one small line coming out. Okay, from 1, 2, 3, 4. These are the 4 external points. And this is the internal point. This is hi. This is representing a factor, an hi or phi to the 4, which has 4 lines coming out. And then what is the rule for drawing Feynman diagrams? Namely, you connect these short lines in all possible ways. So this has one line coming out from each of these and 4 lines coming out from here. So this is one way of joining. This is another way of joining, right? You join 1 to 2, you join 3 to one of these, 4 to one of these, and then this, and then of course you can permute 1, 2, 3, 4. Okay, I have not written those diagrams, but those are also individual diagrams. Or you can connect 1 to 2, 3 to 4, okay, and you join 2 lines coming out from here to each other, 2 lines coming out from here to each other. Okay. These are the 3 classes of Feynman diagrams that you can draw. Is this point clear? Is it clear that there are no other kind of Feynman diagrams except for permutations of 1, 2, 3, 4?
The loop at sir.
Yes.
Loop at internal point is considered as 2 lines.
Yes. So here the loop means that you have 2 lines coming out from here, right? Okay. And you have just joined them to each other. So you are supposed to join all short lines by some long line, right? Okay. So to begin with, okay, let me again try to write this. Okay. So to begin with, we had this picture. Okay. So we had 4 external lines. Okay. And then you had an inside line, okay, which has 4 short lines coming out. Okay. So this is representing the phi I to the 4. Okay. And the rule for drawing Feynman diagram is that you draw it in all possible ways. Okay. So the second diagram that you saw, right, what I have done there, okay, is that I have joined these 2. Okay. I have joined one of this short line to one of short line here, this short line to this short line here, okay, and then these 2 I have joined together. Right? That's the meaning of a loop. Okay, that I have just decided to join this. This means that I have picked up a delta f of xx. Okay, I think that may become clear when you look at the expression. Yeah, okay. So let's look at the expression for B. Okay, so here, okay, we have a delta f x1, x2. Okay, so this represents this term, delta f x1, x2, delta f x, x3, right? This I am calling x. So there is a propagator connecting x to x3. So delta f x, x3, and delta f x, x4. Okay, there is another propagator connecting x and x4. And now we have a delta f xx because one x has been connected to itself. Okay, so that's the meaning of a loop. Okay, so this loop represents as delta f xx. Similarly, here you have 2 factors of delta f xx, right? You can see that the expression for C, 2 factors of delta f xx. Is this clear?
Yes, sir.
So Feynman diagrams are just different ways of representing what you already had here, right? If you had just applied this formula blindly, right, you will get many terms. Feynman diagrams are just encoding those terms, right, in a diagrammatic form. But if you want the hard way, right, and evaluate all of these terms, you will get exactly the same expression that we'll be writing down in terms of Feynman diagrams. Okay. So here, for example, okay, the expression corresponding to this involves a d4x, okay, because this is an internal point. Okay, you have integral over x. Okay. Then you have delta of x x1, delta of x x2, delta of x x3, delta of x x4. Okay. There is only one lambda, so 1 over m factorial is 1 over 1 factorial. That factor is not there, so you have minus I lambda over 4 factorial. And now this one is what is called a combinatoric factor. This tells us how many ways this diagram can actually appear. So let me try to explain how that happens, and maybe tomorrow I'll try to go through it again. So the way you count this is that you start by drawing this diagram that we drew on the screen. Okay, that there are 4 lines coming out from the 4 external points and 4 lines coming out from the internal point. And then you are supposed to find out in how many ways you could have reproduced this diagram by joining those lines. And the counting here goes as follows. You start with 1. See this one, okay, according to this diagram, one has to join some line coming out of the 4-point vortex. But there are 4 lines coming out of the 4-point vortex, right? So one could have joined to one of those 4. So it could have been done in 4 different ways. So that's this factor of 4. So once you have fixed that, you look at how many ways 2 could have connected, right? 2 of course have to again connect to the internal vortex, right? That's this diagram represents. That's what this diagram represents. So 2 could have connected in 3 different ways because 1 line is already gone, right? That has connected to 1, 3 lines left over. So 2 could have connected to any one of those 3 lines. That's this factor of 3. Then 3 could have connected to any one of the 2 leftover lines. That's this factor. And then 4 has no choice. It has to connect to the remaining one. So that's this combinatoric factor of 4 times 3 times 2. So let me explain the counting for these 2. So from B, for example, this factor is common. Okay, these are again straightforward, just propagators. Now here you look at 1. 1 has no choice. It has to join 2, right? 1 has 1 line coming out, 2 has 1 line coming out, and they are joined to each other. So there is no choice here. Now 3 has to join to one of the 4 lines coming out of this vortex, and that can happen in 4 different ways. That's this factor of 4. Then 4 has to join to the remaining lines, 3 lines left over. Right? So 4 can join to any of these 3. That's this factor of 3. Once that has happened, okay, you have 2 lines remaining from here, and they have to join each other. Right? That's what this diagram represents. So there is no further choice. So that's why the combinatoric factor here is 4 times 3. Is this counting clear?
Yes, sir.
Okay. And finally, for this one, 1 has to join to 2, it has no choice. 3 has to join to 4, no choice. So you have 4 lines coming out of this. One pair has to join to each other, the other pair has to join to each other, right? So here the only choice is, right, that let's take any one of those 4 lines coming out, right? How many choices does it have? It has 3 lines, other lines. It could join to any one of those 3. You join that to one of these 3, right? That gives a factor of 3. Once that has happened, okay, there is no further choice. The other 2 lines have to join each other. Right? So here the combinatoric factor is only 3. And that's what you have here. Now I should say that this contribution from diagram B, right? Of course, this is a contribution, but there are other diagrams of the same kind, right? This 1, 2 could have been replaced by 2, 3 or 3, 4. Those are different expressions, right? Because that will not give the same expression. That's why it's not counted in the combinatoric factor. But you should keep in mind that there are actually 6 diagrams altogether of this kind. and altogether 3 diagrams of this kind. Okay, and all of those have to be added up together to get the expression for the numerator for n equal to 4 and m equal to 1. Okay. But we'll go through this again tomorrow. Okay. But I think it's important that you understand how to count, how to analyze Feynman diagrams. Okay. So I think I'll stop here. Are there questions?
Sir?
Yes.
I have a different question. When we were solving the free field theory,
Yes.
we solved for phi, let's say, and like we didn't impose any initial conditions. We imposed commutation relations, and that sort of fixed the field completely.
Well, it didn't fix the field completely. I mean, what we calculated is are the expectation value in the ground state, right?
Yeah.
See, it's like suppose you have a harmonic oscillator.
Yeah.
When you try to solve classical equations of motion, of course, you have to give a boundary condition, right?
Yeah.
But suppose you want to calculate the expectation value of time order product of QT1 to QTN, right?
Yes.
In the vacuum. That is a completely well-defined question, right? You don't need any boundary condition for that.
Yeah.
Right? The fact that you are calculating the expectation value in the vacuum, in a sense, that is the boundary, that is the analog of the boundary condition, right? That's the state in which you are calculating the expectation value.
Okay.
Right?
So
in this sense, you shouldn't think of the field theory as very different from quantum mechanics.
yeah, so like here the question is when we were solving this interacting theory, we imposed a condition that given we have phi and pi at some time t naught, and then we are evolving these fields for arbitrary time.
Yes.
So although we get same solutions because the commutation relation fixes them, and we get whenever we compute these correlation functions, we get them in terms of delta f.
Yes.
But those two initial fields could be quite different. For like we could choose two different fields for which we get the same kind of correlation functions.
Yes.
So like, is that true? Like the field, like in some sense, are arbitrary, I'm saying.
Yeah. See, the point is ultimately, if you look at this expression, right, nothing depends on T naught, right?
Yeah.
U T prime doesn't depend on T naught, right? So it's not that we started by fixing the fields at T naught and evolved from there, right? It was a definition of an operator, right, phi I, that we introduced.
The correlation functions won't depend on these like the fields that we have defined at T equals T naught, but like the field, like the evolved field, like the interaction.
Phi I. You are saying the phi I depends on T naught.
Yeah.
Yeah, certainly. Phi I does depend on T naught.
The unitary operators will also depend on that field.
Yeah, ut will depend on T naught, but not utt prime.
That will also depend, right?
No, see, utt prime, let's look at
because
the
it came in the differential equation. We were using hi t, and hi was defined in terms of t naught, phi t naught.
Okay, yeah. So in that sense, you can say it will depend on T naught. Yes, okay.
Yeah, so like the fields can be anything, but the correlation functions that we are getting are sort of fixed by the commutation relations that we impose on them.
Exactly, yeah.
Yeah, so yeah, that's what I'm asking. Is there, can it be true, or like can we could say like in normal quantum mechanics we could say this that like we are sort of making a canonical transformation between fields. Like initially we could let's say we are doing the harmonic oscillator, and initially we had phi, like x and p, and we could do a canonical transformation by like transforming x to p and p to minus x.
Okay.
And that would fix, although the fields are quite different now, but we are getting the same correlation function even there.
Okay, yes.
So can we do this in quantum field theory for two different fields? for which we are getting same kind of correlation functions.
Yeah, see, okay, here we don't really have to think in terms of canonical transformation, right? Because imagine that how phi I, suppose you change T naught, okay?
Yeah.
Suppose, so phi I T naught, I agree that it depends on the definition of T naught, right? But phi T naught and phi of any other point, time T naught prime, is related by conjugation by e to the IH T naught minus T naught prime, right?
But even H was defined in terms of phi T naught and phi T naught. We wrote phi T naught
But A,
square.
see, H was defined before you even introduce T naught, right? H is the Hamiltonian, full Hamiltonian.
Can you go to the expression
Yes.
of H?
H was this, sum of these two.
Yeah.
Right.
And we said the H free plus H interaction.
Yes.
This will be conserved at any time t.
Yes.
And we chose H at time t naught. And H at time t naught was defined with phi t naught and phi t naught.
But the definition of H didn't depend on T naught, right?
Yeah, that did not depend on T naught, but that depended on phi. And phi.
Depended on phi, but not on phi I.
Yeah. Yeah, I'm not talking about time. I'm talking about the fields. We could have chosen some completely different field and its conjugate momentum.
I mean, are you saying that if you, instead of phi, if you say define a new field phi as phi equal to chi plus chi square?
Yeah.
That's a kind of transformation you are thinking about?
Yeah.
Okay, so that has nothing to do with T naught, right? It's
no,
just that if you use a different field, phi equal to chi plus chi square. Okay, yeah. So if you do phi equal to chi plus chi square, right, then what one can show is that in general, the theory may change. Okay, just like in under canonical transformation, you know, in quantum, in classical mechanics, if you make a general canonical transformation, right, the theory can change. Yeah. Right, a quantum theory is not necessarily invariant on a canonical transformation, because if you take, say, q tilde, p tilde, which are canonically related to qp, the commutation relation between q tilde, p tilde agrees with that of qp only to first order index h bar expansion. So there are inequivalent quantization, and that issue is there here also. See, if you rewrite phi as chi plus chi square and try to quantize in terms of chi, then what one can show is that to leading order the theory is the same, but it may start differing at the higher orders in expansion. Okay. Is this clear? See, this problem is there even in quantum mechanics, right? Yeah. Suppose you start with harmonic oscillator, right? And you make a change of variable x equal to y plus y square.
Yeah, that is true, but let's say we had two entirely different fields. Call it phi 1 and phi 2.
Phi 1 and phi 2, yes, okay.
And we have their conjugate momenta, phi 1 and phi 2.
Okay.
So we are writing one theory using phi 1 and phi 1.
Yes.
And another theory using phi 2 and phi 2. But the Hamiltonian is same. The expression for Hamiltonian is same.
So these are two different theories.
Two different theories because we are using two different fields.
Okay.
So
well, two different fields, but the content is the same, right? All correlation functions will be the same in these two theories.
That's what I'm asking. Although all the observables that we can measure are the same, inherently these two theories are quite different. These two theories are sort of different.
Yeah, but the point is, okay, see, in nature, right, you have to decide what are the fields that describe us. Okay? And you have to include all of those fields in your Lagrangian or in the Hamiltonian. Now, if you say that there is another theory with the same field same structure, but you just call them different, right? That's a different theory altogether, right? That's like there are two different quantum mechanical theories, right? One with QP, another with Q prime P prime.
Yeah.
Right? So they are just two different quantum field theories altogether, just like there can be two different quantum mechanics.
Okay. Yeah.
Or maybe I'm not quite following your question.
Yeah, I understood.
Yeah, we can. I mean, continue tomorrow also, right? You can bring it up again tomorrow, right? If then we can try to address this more carefully.
So
Yes.
T0 factors, even though they are present in a lot of intermediate steps, but in the final expression, it does not come out explicitly.
Yes, that's right.
But
Which of
even
course it shouldn't, because ultimately what are we calculating, right? We are calculating the correlation functions, the vacuum expectation value of the product of the phi's, right? And to start with had no T0 dependence, right? T0 is something that we introduce ourselves.
Yeah, so the initial condition that we take on phi, like we define phi of T0 comma R, and with respect to that, we are defining phi I and HI and all those things.
Yes.
But T0 could have been arbitrary. Only, I mean, somewhere, I think it depends. The vacuum 0 that we have defined is for that T0.
Yes, exactly.
But even the vacuum does not like matter in the theory, right? Only when we insert operators,
exactly, yeah. Because the point is, these
output.
are only auxiliary things, right? These are the things that we know how to calculate, right? And we are expressing in terms of these, but ultimately we get some functions. And those functions have no dependence on T0, right? And that better be because those functions ultimately refer to something that shouldn't depend on T0, because we started by writing something that had no T0 dependence, right? It was a vacuum expectation value of product of the phi's.
Yeah.
Yeah, so certainly you shouldn't expect T0 dependence, and we'll see it also explicitly that the final result, right, has no dependence on T0 in terms of Feynman diagrams or in terms of the propagators. Okay, this, for example, knows nothing about T0.
Hello, sir.
Yes, go ahead, please.
If we directly calculate those terms in the perturbation calculation,
yes.
So for n equal to 1 and n equal to 4 and m equal to 1, so we have to couple them in that 8 terms, like 4 phi's and phi i's are there for 4 terms.
Yes.
So we can couple them like for 8C2 terms, like for all the possible coupling.
No, not just 8C2. 8C2 is only for the first one. We did the counting, 2k factorial over 2 to the k times k factorial, right?
Yes.
For the formula, right? This is the number. These many terms you should get. 105. So if you start doing calculation explicitly, right? You have to basically add up these 105 terms, and you will get exactly this expression that you will be finding by Feynman diagrams.
Okay.
Okay, probably I have to stop because the next class is going to start. But any question that you have, we can discuss tomorrow.
So tomorrow is normal class.
Yeah, tomorrow we'll start with a normal class. I'll send out a message. But I think it will be a short class. After that, I'll ask you people to log out, because I'll be meeting with the registered students. But otherwise, it will start as a normal class.